So I would like now to continue with this radiation physics lecture that we were not able to finish last time. And I think we reached approximately this point when we were now, after having studied the problem of the build-up, we can now fully understand the depth dose distribution for an X-ray curve, which will be always characterized by a build-up region, a maximum dose, and then by the exponential decay, which is typical of every type of radiation. Now, if we go to the low, of course, how steep is this curve depends on the energy. So if we go to low energy, like in diagnostic, this is very steep. I mean, it goes very quickly to zero. It's very easy to shield. If we go to high energy beams that are generally used in therapy, they are much more flat. And this can be seen even better here. You see where we have the cobalt 60, this is the depth in centimeter here, and this is the percent of the dose. Cobalt 60 that was used for therapy for many years is here. These are high voltage with different screen in aluminum and copper. And these are more typical therapeutic beams, 6 MeV, which is probably the most used these days for radiotherapy, 10 MeV and 15 MeV. That, however, they look better. They are less steep than 6 MeV, but don't forget that when you are in this region, you start to produce photoneutrons. So a few words now on the electron interaction in matter. This is actually important because any kind of radiation eventually produce electrons, and eventually will be the electrons to release most of the energy, because, you know, photons produce electrons either by photoelectric effect or by Compton effect or by pair production. But also charged particles by ionization produce electrons, and also neutrons produce, okay, not directly electrons, they will produce protons, but then these protons by ionization will produce electrons. So electron, eventually all kind of interaction, when we talk about the energy released, we always have to talk about electrons. In fact, let's say there are, of course, 2 points. One is the ionization of the molecule, where the binding electron is released, and then you produce these high energy electrons that will undergo further interactions. They can also have additional ionizations. As usual, you can have excitation. You can have excitation will not be interesting for the biological effects per se, as well as the elastic scattering, which is very relevant for electrons, because of course the mass of the electrons is the same of the mass of everything, almost everything else in the matter. So you have a lot of scattering, but it's the inelastic scattering that you actually have a release of energy. So the elastic scattering essentially gives you only a change of direction, but in the inelastic scattering, you have that the initial electron lose some energy, releasing a new electron. So this is the ionization, of course. And the energy, the kinetic energy of the electron produced by the interaction will be given by the primary energy minus the binding energy of the electron itself. Now, how is the cross section for elastic interaction of the electrons? This is the blue line. For excitation, this is the green line. And for ionization, this is the red line. This is an interesting range of energies, because you see you are between 0.01 keV. So this is relatively low energy. In fact, you see the threshold for ionization in water, of course, we're talking about in water here. So the threshold for ionization in water is close to 20 electron volt, let's say. This is the threshold for ionization. Otherwise, it would be impossible to ionize a molecule. And this one goes up, you see, to 10 kilo electron volt, which is generally, even for heavier ions, we will see that most of the electrons are produced in this energy range. That this is the energy which is released in every interaction. Even if the initial particle has a very high energy, the release in the individual impact will be in this energy range. So what is interesting to observe in this plot is that the elastic cross-section just decreases. This is a log-log scale, of course. So the elastic cross-section decreases essentially exponentially, as you could expect. I mean, the elastic cross-section goes down and down and down. The higher is the energy, the lower is the probability of elastic scattering. For the excitation, the situation is similar, but of course in this region here, you have some kind of resonance events. You know, when you, for example, here, when you start to lose, to increase, you see, this is now going down, the excitation, then you start to have ionization. So this goes up again, and then it decreases again at high energy, while for ionization, we have now the threshold for ionization. Then this goes up because increasing the energy, you have now more chance to get ionization until a maximum. And the maximum is around 100 electron volt, you see, maximum is here. Then again, the cross-section for ionization starts to decrease as a function of the energy, as all cross-sections. Simply, you increase the velocity, and then you reduce the probability of interaction because you are a higher velocity. But you see that unlike the scattering cross-section, the ionization cross-section is a maximum, because of course it must start from zero when you have not enough energy to induce ionization. Now, the ionization cross-section for electrons are extremely important if you want to describe on the microscopic and nanoscopic scale how the radiation expands in matter. You know, eventually you have to go to the electrons, and then eventually you have to use the cross-section for ionization. There are several models. One of the most well-known model is the so-called Rudd equations model that you see here. These are differential equations, of course, are not easy. The quantity T and W you see are dimensionless, but capital T is the energy of the primary electron, and capital W is the energy of the ejected electrons, and Li is I here is the binding energy of the electron in the ith molecular orbital. So you get these differential equations, not exactly easy, but of course these are solvable from the numerical point of view. And you see there are many different models, you see, to describe this electron ionization cross-section. You see, this comes from a recent work. You see this solid line is this new model that there are not many experimental data. As you see, these points are experimental data of the ionization cross-section where the model can be benchmarked. As you see, there are several models here. Partrek and Norek are Monte Carlo models. Rudd, relativistic, with the relativistic correction, is more analytical model, and same for the Seltzer model. This is a log-log scale, so this looks like small differences, but they are not so small, actually. This is in the very low energy region here, essentially just above the threshold. All models agree, of course, that the maximum is around 100 MeV. What happens then, you see, in the very high energy region, so when you go to electrons with over 1 MeV in energy, however, you need relativistic correction. You see, for example, in this I believe this is the Busis model that has no relativistic correction, that this will keep dropping, but because of the relativistic correction, you have instead an increase. And even, you see, even you can have not only plateaus, but slightly increase at higher density. This is the same for charged particles. And just to explain it in easy words, I told you that the reason why the cross-section decrease is simply that you increase the velocity. If you increase the velocity, you reduce the interaction time. And then, of course, you will release, you will reduce the probability of releasing a momentum. This will be the delta P on delta T, if you want. Now, however, if you go to relativistic energy, you have a sort of time dilatation. So now the time starts to be increasing again, and this causes the plateau and even a slight increase in the cross-section when you go to very high energy. Here we are, you see, at 100 MeV electrons, which are of course not common, not commonly produced, of course, by photons or even by heavy ions, but you can accelerate electrons at this energy. For example, of course, to do radiotherapy, you need the electrons accelerated in the MeV region. So you are in this region. And these electron accelerators are called LINACs, linear accelerators, LINACs. So, of course, the mean free path of the electron is particularly complicated because, as I told you, this is, you see, a very old cloud chamber image of a path of an electron. And if you go to understand what is happening here, you see that many things are happening. I mean, this was a high energy electron, but then you have Bremsstrahlung, you have elastic scattering. At the end, you have the production of delta rays. So you have this original electron produce new electrons by ionization itself. So you see, for an electron of 1 MeV, the integral path is around 5 millimeters, and it produces around 40,000 ionization in water. So it's only 5 millimeters. So you understand that, for example, doing radiotherapy with electrons is very difficult because the path is very, very small. So you can only do it if it is a very superficial tumor. You have to go higher than 1 MeV. You can go higher than 1 MeV, but still you will have a very low penetrance. And this is the formula that gives you the mean free path, which is, of course, inversely related. This is just the number of electrons per unit volume, and this is the cross section that we have seen before, as described in the Rudd model. So it is quite interesting to see how is the behavior of the mean free path. This is the mean free path in water as a function of the energy. And this is in micrograms per square centimeter. In water, of course, you have 1 gram per cubic centimeter. It is particularly interesting, you see, because okay, the green one is the total, and the red one is the excitation, and the black one is the ionization mean free path. Why is interesting? You see, of course, the minimum of the ionization mean free path approximately corresponds to the maximum, in fact, does corresponds to the maximum of the cross section. And in fact, you see, is around 100 electron volt. But what is, and then of course, when the cross section goes down, the mean free path goes up. And when the cross-section drops, the mean free path, of course, increase. So it's essentially the mirror image, if you want, of the cross-section. But numerically, it's very interesting, you see, because this is approximately, this value here, the value here of the minimum corresponds to approximately 1 nanometer. And this means that the mean free path of the electrons at their maximum cross-section is approximately in the order of the thickness of a DNA molecule. And this is interesting because you can imagine that they have a very high probability of doing ionization, and their mean free path is in the order of the thickness of the DNA. So it's very likely that they induce damage in the DNA in both strands, inducing what is known as a DNA double-strand break, which is the most important lesion for radiation biology, and then for radiation protection and for radiation therapy. Okay, the final chapter that I wanted to touch on in this part, in the next lecture, we will go to charged particles. Now we stay in, let's say, neutral particles, with the exception of the electrons that are, of course, that are important for everything, are the neutrons. So neutrons, again, which kind of interaction can neutron have with matter? They have scattering, which is elastic, and they have inelastic scattering. So the elastic scattering, this is a comparison, let's say, between photons. You see where you have the photoelectric and you have the Compton scattering. Here you have okay, this is an incident neutron with this energy, but then you have two important effects here. One can be the scattering, inelastic scattering, which can be endothermic, so the nucleus is left excited and returns to the ground state by emitting gamma rays, like an atom, if you want. But you can also have absorption of neutrons. This happens when the neutrons have low energy, and then it can absorb, and this can cause the fission of the heavy nucleus that absorbs this thermal neutron. Important. Sorry if I go back. The important thing to remember is that, you see, photons almost always interact with electrons. You remember that you can have also photonuclear interactions with production of neutrons, or photonuclear disintegration, but it's much more likely that you have an interaction with the electrons. Neutrons cannot have any kind of interaction with electrons because they are hadrons, electrons are leptons. They have no charge, and electrons are charged. So the only type of interaction that neutrons can have is with other hadrons through the strong force. So they have to hit, they have to go close enough, let's say, to the nuclei to induce an effect. As you can easily imagine, because the sides of the nuclei is much smaller than the sides of an atom, the cross-section of ionization will be much higher than the cross-section for neutron interaction that are strongly dependent on the sides of the nucleus itself. So, of course, this is what happens when you have a scattering of neutrons. Now you have an incident, an incoming neutron, and then you will have a scattered neutrons with an energy which, if it is in elastic scattering, the energy and the momentum will be now reduced, and then you will have a recoiling nucleus with another angle. The theta angle is the scattering, inelastic scattering angle in this configuration. Now, of course, you can easily describe the scattering. This is classical mechanics. There is absolutely no difference. So you have to use the conservation of momentum and the conservation of energy, of course. And you can have the maximum and minimum energies here. The maximum, this will be generally speaking, let's say the law of cosines describes the energy of the scattered neutrons through this equation. A is the atomic number of the target nucleus, and E is the energy of the incident neutron. And the minimum, as usual, you get it for head-on collisions, let's say, where the neutrons is essentially is backscattered at pi, and then this formula becomes very simple because it's simply given by this equation, a minus 1 divided by a plus 1 to the square, times the incident energy, of course. Now, considering the interaction with protons, if you produce protons, so if you give energy to a proton, let's say that you are in water and you scatter with a proton, then you will have now recoil proton, and the recoil proton energies will be between 0 and the energy of the neutron, depending on how much energy is released in the collision. As a result, neutrons of the same energy can deliver different doses to tissue or any kind of target. 85–90% of first collision dose from neutrons in human comes from the scattering neutron and protons. So essentially, it is the scattering of the neutrons on the protons that cause the energy release, and the energy release comes really from the proton, from the recoil proton, not from the energy, from neutron, because then the recoil proton will ionize, generate electrons, and these electrons will then release further energy. Concerning the absorption reactions, there are different types, the exothermic, the N-gamma, charged particles that can be N-alpha or Np, neutron producing that are exothermic, N to N, and of course the fission, where essentially you produce the fission, you know, so you actually break the original nucleus. Absorption of the neutrons will follow exactly the same rules, let's say, of the that we have described many times already. If you assume monoenergetic neutrons in good geometry, let's say, you will have the usual formula of the Lambert-Beer for the absorptions with and you can have this absorption coefficients of the neutrons. Of course, if you go in bad geometry, then you have to consider the build-up factor. The build-up factor for neutrons, if you are in bad geometry, is very high, is in the order of 5. Because, you know, the scattering, let's say, unlike the scattering on electrons, that is a relatively small angle, for neutrons, it's a head-on collision, so the scattering can be a very wide angle. So the build-up factor is much bigger than it normally is for photons. The cross-section as the units of the barn, it's called barn, is 10 to minus 24 square centimeter. One barn is 10 to minus 24 square centimeter, which is approximately the cross-section, the geometrical cross-section of a nucleon. Is indicated by sigma. The macroscopic cross-section is generally given if you take the number of target atoms, then you can have per cubic centimeter. Then you define what is called the macroscopic cross-section, which is in centimeters to minus 1, which is the same as the absorption coefficient for photons. The cross-section for each reaction are adductive, and they are, of course, energy dependent. I mean, this is the example of how they are addictive. You see, you have the total, the different cross-sections will sum up depending on the different processes that the neutrons undergo. And this is interesting. You see, this is now the mass attenuation coefficient. So in centimeter square divided by gram. So if you want, is the attenuation coefficient divided by the density. as a function of the atomic number of the target. So you see that for X-rays, this is relatively simple. You see the mass attenuation coefficient tends to increase with the atomic number of the target. But for neutrons, the situation is completely different. Completely different for thermal neutrons in particular, because these big values, you know, you have huge values, for example, for boron. You have huge values for cadmium, for gadolinium, because these elements are particularly, because of their nuclear structure here, they are particularly sensitive to thermal neutrons. Boron, for example, we will see that the cross-section for thermal neutrons on boron, the cross-section is so incredibly high. You see, it's so much higher than for the other elements that the boron will be broken by the neutron, by the absorption of the neutron in a lithium and then alpha particles at low energy. This can be exploited in cancer therapy. If you could load a tumor with boron 10, then shooting neutrons, you will have a lot of damage in the tumor because you actually break the boron in the tumor itself. Neutrons are divided in different regions depending on the energy, and they are very different, let's say. Generally, people speak about fast neutrons every time you have energies greater than 0.1 MeV or 1 MeV. In therapy, for example, for fast neutron therapy, people use neutrons in the order of 20 MeV, and even higher energies can be seen in space. For example, when you have shielding of very energetic particles, you can produce neutrons that are even faster. So they are very fast neutrons. Slow neutrons are those between 10 and 100 kilo electron volt, sorry. Epithermal neutrons are those between 0.025 electron volt and 1 electron volt. Thermal neutrons are those in the order of 25 millielectron volt. 25 millielectron volt, as you know, is the kinetic energy of a monoenergetic gas at room temperature. So if you take the air in your room at room temperature, the kinetic energy is approximately 25 millielectron volt. So neutrons with that kind of energy, around 25 millielectron volt, a little bit higher, they are called epithermal, so almost thermal, let's say, are called thermal neutrons. But for your curiosity, I mean, even if it looks like they are slow because they are, you know, it's the air around you, the velocity is quite significant. It's in the order, you see, of 2.2 kilometers per second. So it's not so slow, let's put it this way. And then you can have, of course, cold neutrons, and cold neutrons are those below thermal neutrons, down to essentially almost stopping particles, you know, the extremely low temperature. For the cross-section, as I said, I mean, this is an example that shows, you know, the cross-section from thermal to fast. As usual, the cross-section decreases as a function of the energy, but you have resonances. You have resonances around the region of the epithermal and slow neutrons. You can have resonances depending on the target nucleus that are resonances where the neutrons can be absorbed and induce a fission reaction. It is very practical. Let's say that there are many, I mean, these kind of calculations for the neutron cross sections are extremely complicated, of course, but most numbers are tabulated, you know. And one good, for example, useful numbers for the exercises, you see, is to look at the removal cross section. So this is the cross section that you want to know if you want to know how many neutrons are lost. This is the removal cross section for thermal and epithermal neutrons approximately, you see, in different materials, water, iron, two types of concrete, the ordinary concrete and barytes concrete, and in carbon, in graphite. And you see these are values in centimeter to -1 that you can easily use to calculate the number of neutrons that are found behind the given thickness of this material. Please note, of course, that for neutrons, water is pretty good. The per centimeter, you see, water is 0.1, which is somehow surprising. I mean, if you do the mass coefficient, so if you divide this one by the density, you will see that the absorption, the removal cross-section for water is much higher than the removal cross-section for iron, ordinary concrete, and so on. But that's because water is very much rich in protons. I mean, it's as free protons where the neutron can easily interact. So the cross-section per unit mass turns out to be higher for the light elements like water. Then, of course, you can have more accurate calculations of the mass attenuation coefficient, as I was telling you before. And there are rules. Let's say, for example, for fast neutrons, Schaffer produced some equations that can give you the mass attenuation coefficient in different materials, depending, you see, on the atomic number and on the mass number of the material, that give you approximate values of the mass attenuation coefficient in different materials. This applies for fast neutrons, where somehow you have, for fast neutrons, the cross-section will be more flat, will essentially depend mostly on the sides of the nucleus. This is then the difference, if you want, in a graphical point of view. When you have gamma rays, you see the gamma rays go through paper, they go through aluminum, but they are stopped in lead. Fast neutrons, you see, go through cadmium, go even through lead, but can be stopped by water with boric acid. That's again an example where they can be stopped in concrete, but you need very thick concrete, of course. And here you have another example where you take fast neutron, then you slow down the fast neutrons in water. Then essentially you use water as a moderator. Now you have thermal neutrons, and now the thermal neutrons, you can stop them in cadmium. So clearly the shielding of neutrons as a medical physics problem is much more complex than the shielding of photons, because now the type of interaction is more complicated. The energy dependence is critical. So sometimes, rather than using extremely thick blocks of concrete, can be, as happens in neutron reactors, for example, can be much better to moderate the neutrons in water, and then it will be easier to stop them. Concerning the neutron dose, so how to calculate the neutron dose, this is also important, because you see the cross-sections are low, so you need a lot of neutrons to release high doses. You need to know the fluence, of course. So how many neutrons per square centimeter and per second, that would be the flux you have, and their energy, because the release depends on the energy. You need to know the distribution of atoms in the material, the interaction cross-section, and the amount of energy given to charged particles created by neutron interaction. So this is summarized, let's say, in this formula that is actually, this is the flux, this is the number of nuclei per unit volume, this is the cross-section, this is the average energy released, and this is the density of the material. So to calculate the dose from neutrons, you need these quantities, and you see, for example, the Q average is non-obvious, of course, and the sigma is also non-obvious, as we have seen before. But there are nice tables, again, that allows you to convert neutron fluents to those. These are, for example, examples of neutron energy for thermal neutrons, and then faster neutrons. You know, these are neutron up to 1 GeV, and gives you how to convert the fluents to those. This is the fluents per square centimeter of neutrons necessary to give you 1 centigrade of those in water. The other problem is that, of course, we have seen this already. The dose per se does not give you the sievert, which is the quantity that you need in radiation protection. And the relationship between the neutron energy and the radiation weighting factor is quite complicated, you see, because at very low energy in the thermal and epithermal region, the quality factor is approximately 2.5, but then it becomes much bigger in the order of the MeV. MeV are the so-called fission spectrum neutrons. When you make fission, normally the neutrons have a spectrum, of course, a very wide spectrum, but the spectrum is peaked around 1 MeV. And this energy of the neutrons is the one particularly effective in inducing biological damage. You see, the weighting factor is about 20, so this means that 1 gray corresponds to 20 sievert. Then when you go to fast neutrons, the weighting factor decreases again, you see, and goes back to a value approximately somewhere in between 2 and 3 when you go to very, very fast neutrons. And the flux to equivalent dose conversion, I gave you some values before, but the calculation, this is the picosievert per square centimeter, and this is the energy in electron volt. You see, it's very much energy dependent here. It gives you the idea of how the calculation of the released energy is complicated for neutrons. For fission, I told you, the fission, we will not touch very much fission in this lecture, because in this course, because this is more, we do more in the course in radiation biophysics for the implication in nuclear terrorism. But in any case, you should know, I mean, that the material for fission are divided in fissionable, that are those isotopes that will fission only when struck by a very energetic neutron, typically uranium-238. So it's not practical uranium-238 for doing a nuclear reactor or a nuclear bomb. Vice versa, the fissile isotopes are those where even a neutron with almost, let's say, cold neutron, even a cold neutron can induce a fission. And this is the neutron, the isotope, the rare isotope of the uranium-238, which is 235. So if you want to do nuclear energy or nuclear bombs, you need to isolate from the great mass of 238 the few to enrich the uranium. Let's say you have to enrich the uranium with the isotope 235. And finally, you can have fertile isotopes that are those that produce a fissile isotope after absorption of a neutron, and this is the case, for example, of thorium-232. This is the mechanism, let's say, in general, that you have when the energy released in the fission process is tremendous, of course, because you have the full energy of the nuclear structure of these very heavy elements is now released in the fission. You produce many radioactive elements, and you produce more neutrons. So if you are within the so-called critical mass, you can have a chain reaction when you have fission and fission and fission. So the neutrons escaping the volume are not enough, let's say, to stop the chain, so that you can keep the chain going on, and then you can produce a very large amount of energy, like in a nuclear reactor or in the nuclear bomb. Okay, with this I will stop. We will, you will find this lecture along with a few exercises that apply to all this first lecture that unfortunately was done in 3 chunks. I apologize for that. You will find it on Moodle. And then on Friday, let me just make sure I say that. Yeah, Friday the 13th at 3:20, we will have our question and answer, where you can ask me questions on the lecture. And also I would like you to have a look to the exercises, so that we can tell me whether you had, I'll try to give you many exercises this time, so that you can also choose which one you want to do, and we can discuss together how to solve these exercises. Thank you very much.